So I invite you all for the first National Mathematics Day, which is being celebrated in our institute. And we are very lucky to have with us Professor Ram Murty, who is going to give the first talk of this session, of this National Mathematics Day in our institute. So I think most of the people in the audience, they do not need introduction of Professor Ram Murty. However, there are some for whom I will just read out a brief, few sentences about him. And the details you can see in his web page. So Professor Ram Murty obtained his PhD from Massachusetts Institute of Technology, MIT, in the year 1980. And during 80 to 82, he was a member of Institute of Advanced Studies, IIS Princeton, and also TIFR, Tata Institute of Fundamental Research. Currently, he is holding the Queen's Research Chair at Queen's University, Kingston, Canada. He has earned several prestigious awards and the elected member of several prestigious academies. I can't list them. Briefly, in 2008, he was elected as Fellow of Indian National Science Academy, INSA. In 2013, he was awarded the Simons Fellowship. Very recently, just in November, he was conferred the Best Research Guide Award by Queen's University for thesis supervision. This is something that we don't have in our country, all right? So this is a news, this is a good news. His main research interests are number theory and philosophy, particularly Indian philosophy. In mathematics, he has written more than 250 papers, research papers, as on date. Next time when we see it, maybe 300. So, is a constant producer of ideas and papers of highest quality. And he has written more than a dozen books, and one including on Indian philosophy. He's also an adjunct professor at various institutes in our country, like our institute, TIFR, HRI, CMI, IIT Mumbai, and ISER Bhopal. And I'm very happy to be associated with him for the past 5 years. Okay, it has been a very nice and productive friendship and relationship, very warm. His personality is so strong and so magic that, it's like, he's like that uncle who comes to our home once in a while with a lot of chocolates, and we look forward for, the kids look forward for them. And he's like that brother who will say that, don't worry, I am around, all right? So he gives that kind of confidence and encouragement. And for friends, he will always say, all is well, all is well, all right? Now, I invite Professor Ram Murty to kindly take over and please start your talk. Thank you very much, Professor Ram Murty.
Thank you very much, Professor Srinivas. Do I use this or can I use this? Okay. Yeah, this is working. I can speak through here. Is it everybody can hear me? No, this is fine. This is fine. Can everybody hear me? You're not audible? No. How about this? Can you hear me now? Okay. Okay. Well, thank you very much, Professor Srinivas. Thank you to the Institute for Mathematical Sciences for inviting me to speak on this grand occasion of the birthday of Srinivas Ramanujan. It's an honor to be here. So let me begin with some blessings from Ganesha. This is in nearby in Kalahasti, the temple near Kalahasti. The story of Ramanujan is really a story from rags to mathematical riches. And in 1919, Robert Canigal wrote the first definitive biography of Ramanujan. So there's Robert Canigal, that's his book. And it was full of interesting stories and formulas. So The Man Who Knew Infinity, that was the title of Canigal's book, and they managed to make a movie out of it. And most likely, most of you have seen this movie. For a Hollywood production, it's not bad. So the birthplace of Ramanujan, there it is. That's the house. He was born on December 22nd, 1887 in Erode, Tamil Nadu. This is a photograph of the town. As you can see, it's a temple town. The story of Ramanujan is quite inspiring by anyone's account. To a large extent, it's inspiring because he was self-taught and became a universal genius with his fundamental contributions to number theory. This talk is a panoramic view of how this came about. The other interesting aspect of Ramanujan's life story is the fact that it happened during the colonial rule of India. So I think against the backdrop of the British rule of India, here was a person who came essentially from the dust of India and showed that we can be as valuable to the future of civilization in mathematical genius as any other nation can be. So that's the place where he was born. In his childhood, he showed a keen interest for mathematics. At the age of 12, he borrowed a book called Loney's Plane Trigonometry. There's the book. He took it from an older student and completely mastered its contents. Now, most of the time when we think of trigonometry, we think it doesn't include calculus, but this particular book goes far beyond the standard trigonometry and also treats the rudiments of calculus. The book that changed his life, I suppose, is this book called Carr's Synopsis. And Carr's Synopsis of Pure Mathematics is a book that Ramanujan borrowed from the local library, and he delighted in proving the results contained there. Now, the Carr's Synopsis is a manual that was used by people who were preparing for the tripos examinations at Cambridge University. It was not a book which was an instruction manual of any sorts, but rather a collection of theorems. And Ramanujan took it as a book of problems and actually started to prove each theorem. And of course, he didn't waste paper. He used this slate. So he would use the slate to do the problems and rub the slate off with his elbow. And story is that he had a bruised elbow all his life. And we now know how he got the bruised elbow. Now, his college days were not all that great. In 1903, at the age of 15, he was admitted to the government college in Kumbakonam, but failed his exams because he spent too much time in mathematics and neglected his other subjects. Having failed in Kumbakonam, he moved to Madras, or Chennai as it's called now, where he enrolled in Pachayappa's college. But again, he failed due to his neglect of his non-mathematical subjects. There's even a story of the time that he ran away from home. Apparently, here's an entry in the Hindu newspaper. A Brahmin boy of the Vaishnava sect named Ramanujan, of fair complexion and age about 18 years, was till recently a student of Kumbakonam College. He left his home on some misunderstanding. His guardian is very solicitous about the boy's returning home. He stayed at Rajamundry for about a month and was last seen there some 5 days back. Those who happened to see him are kindly requested to persuade him to return home and to communicate his whereabouts. So this is a kind of an interesting tidbit of new history that we did not know about. As a clerk in the office, in the Port Trust office, so because of his failed exams, he couldn't get his degree. He was accepted as he accepted a job as a Port Trust in the Port Trust office as a clerk, and he tutored students on the side in mathematics and somehow eked out an existence. But he found leisure to do mathematics and jotted down his results in his now famous notebooks. So these are the Ramanujan notebooks that now are well known. Now, two Indian mathematicians in Chennai by the name of Ramachandra Rao and Seshu Iyer both helped Ramanujan and discussed numerous mathematical ideas with him in 1910. In fact, it was Iyer who suggested that Ramanujan write to G.H. Hardy and other mathematicians. So the story of Ramanujan writing to other mathematicians is an interesting one, and I thought I would document that for you here. So first, Ramanujan's work was shown to this person by the name of M.J.M. Hill. There he is. So several British professors in India were showed some of Ramanujan's work, and looking at Ramanujan's work on divergent series, Hill remarked that he has some taste for mathematics but should study more, and so recommended a few books. I think the thing that caught Hill by surprise, perhaps, was the equation that 1 plus 2 plus 3 plus 4 plus ... is equal to minus 1 over 12, which was a famous formula of Ramanujan. You obtain it through analytic continuation of the Riemann zeta function, and it's a well-known formula, but apparently Hill thought this person doesn't know anything about convergent series. So he dismissed Ramanujan's work as being irrelevant. Then he sent his work to H.F. Baker and E.W. Hobson. So there's Baker, there's Hobson. Neither of them responded to Ramanujan. So they will go down in history as two more cases of missed opportunities. The famous letter of Ramanujan to G.H. Hardy, of course, is well known. It was written on the 16th of January 1913. That was a turning point. After a brief introductory paragraph, the letter lists theorems and formulas for the next 10 pages. So there's G.H. Hardy, and there's the first page of the letter. Notice the beautiful handwriting. Penmanship is something that unfortunately students are not able to cultivate these days. Here are a few sample pages from the letter. As I said, it was full of formulas. Here are some formulas listed. Of course, he wrote these all by hand. This is a printed transcript of the letter that appears in the collected papers of Ramanujan. So when Hardy received the letter, he could not decide if it was written by a genius or a crank. There were 120 theorems stated in the letter. I want you to pay particular attention to equation formula number 7, because it'll appear in the talk later on. Notice the presence of the hyperbolic functions, the cosine, hyperbolic cosine, hyperbolic sine, that appear in the explicit formula of the coefficient of the reciprocal of a certain theta series. So here are a few extracts from Ramanujan's letters. So as you can see there, formula after formula of beautiful things. Formula like this appears. Another formula, e to the pi square root 58 appears, which is very close to a natural number, 104. And all the reason for this proximity to integers has a lot to do with what's called a theory of complex multiplication. So it was pretty clear that Ramanujan knew what he was doing. Let me draw your attention to one particular formula here, number 3, giving an explicit formula for the number of primes up to x in terms of what's called the logarithmic integral. This is a formula that was first written down by Riemann in his famous 1860 paper on the prime number theory of prime numbers, where he introduced his famous zeta function. But it's amazing because Ramanujan couldn't have possibly read Riemann's paper. Firstly, it was written in German, he couldn't have read it. Secondly, he didn't have access to Riemann's paper. So he derived the same formula that Riemann had on his own. And this is an amazing formula that for him to get. Now, after seeing 10 pages of these mathematical formulas, Hardy's initial reaction can be described as follows. Here's Hardy with Littlewood. Is that picture? It's a very faded picture, isn't it? So after losing sleep that night, Hardy invited his colleague, Littlewood, to come over and have a look at Ramanujan's letter. And after 3 hours, they concluded this was the work of a genius. Hardy wrote, "A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them." The following day, Bertrand Russell, who was also a student at Trinity College at that time, is said to have recorded in his autobiography the following passage. He wrote that by next day he found Hardy and Littlewood in a state of wild excitement because they believed they have found a second Newton, who happens to be a Hindu clerk in Madras making 20 pounds a year. So this is an interesting entry in Russell's autobiography, which is a 3-volume book which is worth reading. So Ramanujan sails to England on the 17th of March, 1914. And he arrived there on the 14th of April, 1914, almost a month after he started. He was seasick for a period of the time. And he was received by Neville in London, with whom he stayed for a few days before taking the train to Cambridge. So here's a picture of Neville. And he stayed in England 5 years and returned to India in 1919. He died a year later at the age of 32. So this is a story of Ramanujan's life. Now, Ramanujan's work in England consists of very voluminous material. From 1914 to 1917, that's only about 3 years, Hardy and Ramanujan had fruitful collaboration. And during that time, they wrote more than 30 papers, 7 of them jointly. Ramanujan wrote 30 papers, 7 of them were jointly with Hardy. We'll highlight here 3, since they shaped the course of the 20th century mathematics. So I'm going to pick 3 of these papers and to highlight them. And I'll try to be as gentle as possible, but I think that since the crowd here is essentially academic, I don't have to have any fear that you will not understand what I'm going to say. So 3 fundamental papers. The first paper is the paper called the normal order method, the normal number of prime factors of n, written in 1917 in the Quarterly Journal of Mathematics. The second paper is essentially the introduction of the famous circle method. It's a joint paper with Hardy called Asymptotic Formula in Combinatory Analysis, published in 1918. This is where the famous partition function appears. Third paper is, of course, the famous paper on Ramanujan's tau function, which is what this talk is going to get focused on. It was modestly called on certain arithmetic functions. This was remarked this morning in Kumar's lecture, and it was a paper written in 1916. And this is where he makes his famous conjectures. Now let me talk a little bit about the normal order method, because I think this is probably the easiest of the 3 papers to explain to the lay audience. So let omega of n be the number of distinct prime divisors of n. You all know that every natural number can be written as a product of prime numbers uniquely, So what we could do is we can count the number of prime divisors that a given number has. Now you can see that a number has only one prime divisor if and only if n is a prime power. And so the question is there any regularity in the behavior of omega of n? And Hardy and Ramanujan came up with this remarkable theorem that usually with the probability 1, omega of n is like log n. In other words, a random number has around log n prime factors. So this is the Hardy-Ramanujan theorem. Let me be a little bit more precise. Fix an epsilon positive. Fix epsilon positive, the number of n less than or equal to x, such that omega of n minus log n is bigger than log n to the half plus epsilon, is little o of x as x tends to infinity. In other words, with probability 1, we have omega of n minus log n less than log n to the half plus epsilon. Now the paper was innovative for its use of the rudimentary sieve method. I should mention here that interestingly enough, this particular paper was assigned to my recent PhD student, and she managed to study it very minutely and noticed that the error terms, the little o of x, can be improved to big O of x over arbitrary powers of log, which was not known before. So she's written a paper, and I think this paper will appear in the Ramanujan journal. Now this particular paper sparked the interest of several people. First, in order of importance, is perhaps Paul Turan, who unfortunately didn't realize the importance of his own work, and it was left to Erdős and Katz to discover this remarkable theorem that omega of n, because it behaves like log n with probability 1, we can look at the deviation from this average, so omega of n minus log n, and divide by the square root of the standard deviation, square root log n, and ask how often is it the case that that quantity lies between a and b for given numbers a and b. And it turns out it's the normal distribution. So the function omega of n obeys a certain normal distribution. This is the beginning of the work. A new branch of mathematics was created by this particular paper. It's the creation of probabilistic number theory, as well as new inspiring sieve methods. And it is largely due to the efforts of Paul Erdős and Mark Katz that we have the grand development of the subject called probabilistic number theory, which seems to marry ideas of probability theory and number theory in a fantastic sort of way. I want to come back to this formula later on in the context of the tau function. The second paper that I talked to you about, that Hardy and Ramanujan wrote, was the paper on the partition function. The function P of n is the number of ways of partitioning a number n. For example, number 4 can be written as 1 plus 1 plus 1 plus 1, or it can be written as 1 plus 1 plus 2, or it can be written as 2 plus 2, or 1 plus 3, or simply 4. Now, we're not counting the arrangement of the things. We're basically looking at distinct partitions in the sense that you can write it as lambda 1 plus lambda 2 plus lambda in a decreasing sort of order. So you can see that the number of partitions of 4 is 5. Now the partition function is very important in physics for a variety of reasons, but it's also important in mathematics, not just number theory. It appears in representation theory. For example, if you want to study the representation theory of the symmetric group, the number of irreducible characters of the symmetric group on n letters is given by the partition function. And then the next question is, that means that every irreducible character corresponds to a particular partition, and is there a natural way of going from the partition to the representation? And the answer is yes, and that's a rich theory, the theory of Young diagrams, which is very important in the context of group representation theory. And then the amazing thing about the partition function is, again, that it appears in the representation theory of GLN. So this, again, these parabolic subgroups that you construct, one parabolic subgroup for each partition. So that's, again, a situation where this is very important. So each partition of n can be factored as k1 plus 2k2 plus 3k3. So you look at how often does 1 appear, that's k1. How often does 2 appear, that's k2. How often does 3 appear, k3. So that's a unique factorization. And using that, you can write down the generating function. I hope this appears. You know what's going on? I think there's a kind of a transition between computer to computer. Some of these, the slides are kind of off phase. I hope it's visible. So it's easy to see now that the partition function has a generating function given by this particular formula. And this is the formula that was mentioned earlier as well in the talks this morning. So can we find a formula for P of n? In 1918, Hardy and Ramanujan discovered, using the circle method, the asymptotic formula, that the partition function has exponential growth. It grows like e to the pi square root 2n over 3 divided by 4n root 3. So it has exponential growth. And in 1937, so just to remember 1918, this is when the paper was written. 1920, Ramanujan dies, and 1937, Hans Rademacher, here he is, gave an explicit formula. See, P of n, an explicit formula for P of n, using the hyperbolic sine function. And the ak of n is a certain exponential sum, and the SMKs are what are called Dedekind sums. So there it is. There's the explicit formula for the partition function. It was discovered by Rademacher in 1937. Now, if you remember, the very first letter that Ramanujan wrote to Hardy contains these hyperbolic sine functions, giving essentially he's talking about the reciprocal of the theta function, trying to say the explicit coefficient is given by some hyperbolic sine function. And so any scholar worthy of their name can see that Ramanujan obviously had an idea about these kind of asymptotic expansions of the Rademacher type. And the person who notices this is Selberg. So let's look at that letter first, and you can see that there it is. There's that formula, if you remember, that first letter of Ramanujan. And Selberg makes the following comments. In the summer of 1937, I had actually myself been studying number 36 in the collected papers of Ramanujan, had arrived at Rademacher's formula. It always seemed strange to me that Hardy and Ramanujan did not end up with this formula, and I believe firmly that the responsibility for this rests with Hardy. So, as I said, any scholar worthy of their name sees that Ramanujan had this formula, and it was, in some sense, the Hardy-Ramanujan formula was an asymptotic formula, whereas the Rademacher formula was an exact formula. And that's and the point is that Selberg notices that Ramanujan essentially had the exact formula, and it was up to Hardy to have encouraged that. But Hardy, being an analyst, and not in some sense a number theorist, as the criticism goes, missed the opportunity to develop the Rademacher style formula. Now, Brunier and Ono in January 2011 discovered a new exact formula which expresses P of n as a finite sum of special values of weak mass forms evaluated at certain CM points in the upper half plane of discriminant minus 24n plus 1. Now this is an interesting thing. So there's a certain modular function of some sorts which if you evaluate it at some special points, it's a finite sum, it actually gives you P of n. And this formula, here's a picture of the group on June 7th, 2003. I was part of a group where we had given lectures on modular forms at Urbana. There's Brunier, and there's Ken Ono. The other people are Jungjo Choi, Winfried Konen, and Masabu Kaneko. And in that year, 2011, this formula was discovered, and of course that gave myself and my postdoc a new idea. So we thought that, hey, you know, if you have a formula, explicit formula for the partition function in terms of special values of some sort of weak Moss form, you should be able to derive the asymptotic formula of Hardy and Ramanujan, or even the Rademacher formula. And sure enough, without using the circle method, we were able to do this. And this is joint work with my former postdoc, Michael Dewar, and myself. Michael Dewar no longer is in mathematics. Apparently he is now in the business world. He's a vice president of a very prominent company that works in China. Now the generating function for the partition function is given by as this infinite product, as I mentioned earlier. The key observation is to put x equals e to the 2 pi I z. I see that fonts are moving around, so I hope it's clear to everybody. That really is an exponential. The right-hand side becomes essentially 1 over eta of z, where eta is the Dedekind zeta function, and eta of z is what's called a modular form of weight 1/2. What does it mean? That means that if I, just bear with me if you are not an expert, this is not that hard to understand. If you take a transformation a tau plus b over c tau plus d and evaluate eta at that point, it transforms very neatly in this fashion for any matrix A, B, C, D in SL2Z. These are matrices, 2 by 2 matrices with determinant 1 and integer entries. And that's the transformation law. And Ramanujan noticed that the partition function is connected with the Dedekind eta function. So there's a modular connection between the partition function and the modular forms. And similarly now, the 1916 paper of Ramanujan outlining properties of the tau function is also going to play an important role in the development of mathematics. Shortly after he made conjectures, Louis Mordell, followed by Eric Hecke, followed by Joe Lehner and Atkin, developed the essential theory of modular forms that Ramanujan had initiated in the 1916 paper. So if some of you had heard the lecture this morning when the results of Atkin-Lehner were mentioned in Biplab Paul's talk, the theorems that he quoted were of a 1976 vintage. So you can see where is 1916 and where is 1976 before the entire theory gets as a complete, comes to a fruition, especially with respect to the theory of Hecke operators. So that's took a grand total of about 60 years to complete. Now, the delta function is essentially the 24th power of the Dedekind eta function. So you will recall I introduced the Dedekind eta function in the context of the partition function. Here now it appears as the 24th power, and that's the definition of these coefficients. So here they are. So Ramanujan was never averse to doing numerical work. So when you take that infinite product and calculate the coefficients, you end up getting this infinite series. Let's see if this pointer works. Oh, good. Okay, so you can all see, let's see if I can put my, speak into the microphone at the same time. So you can all see that the second coefficient is minus 24. The third coefficient is 252. But then Ramanujan notices that if you take this number and multiply it by the third coefficient, you end up getting this one, the sixth coefficient. If you take this coefficient minus 24 and multiply it by the fifth coefficient, you end up getting the 10th one. So he starts seeing patterns. I mean, for us, these are just numbers, but for Ramanujan, they hold patterns. They're key to some deeper aspect. So he notices these things, so he makes these remarkable conjectures. Tau is multiplicative, tau n equals tau of m times tau of n, whenever m and n coprime. Then he writes down a certain second order recurrence, which I will not bother stating right now. And third, he makes his famous conjecture that tau of p is always less than 2 times p to the 11 halves. Now, these are called Ramanujan conjectures. They were formulated by him in 1916, finally resolved in 1974 by Pierre Deligne. Now, interestingly enough, if you go back to the slide where I had put the picture, there's Mordell. There he is, right there. What he does, Mordell's paper of 1917 simply addresses Ramanujan's first two conjectures, and he quickly disposes of it, as it were, in some sense. I believe the attitude could have been a deterrent in the development of number theory, because I think he just thought that it was a special case, peculiar to the tau function. And it was Erich Hecke who developed the theory. Yeah, Erich Hecke who developed the theory of multiplicative coefficients and gave it the proper foundation, but the theory of Hecke was not complete until 1936. So where's 1916 and where's 1936? That's a 20-year gap between the two. It could have been done in 1917, but it wasn't. Now Hardy makes some comments on the tau function. Here's G.H. Hardy. In his 1936 lectures on Ramanujan delivered at Harvard University, Hardy made some comments about the tau function which have become very famous. Let me quote Hardy. He said, "We may seem to be straying into the backwaters of mathematics, but the genesis of tau of n as a coefficient in so fundamental a function compels us to treat it with respect." Okay, so Exhibit A, I put this in front of you. Make sure you understand what Hardy is saying. He's not denigrating the tau function. He just says, we may seem, notice the word we may seem to be straying into the backwaters of mathematics, but the genesis of tau of n as a coefficient in so fundamental a function compels us to treat it with respect. Now, Andre Way, in his 1972 Writ Lectures, makes several pronouncements on what analytic number theory is, and then pounces on Hardy. He wrote, Hardy's remarkable comment is, we seem to have drifted into one of the backwaters of mathematics. To him, it was just another inequality. He found it curious that anyone could get deeply interested in it. In fact, he becomes apologetic and explains that in spite of the apparent lack of interest in this problem, it might still have some features which made it not unworthy of Ramanujan's attention. So Hardy gives a different spin on, Way gives a different spin on Hardy's comment, and I think it's an unfortunate spin. Now, by a strange occurrence, it turns out that Ramanujan's conjecture is connected to the Way conjectures. And the way the Way conjectures were formulated are described by Andre Way himself in his Apprentice of Mathematician. It's kind of semi-autobiography. In 1947, he says, in Chicago, I felt bored and depressed. And not knowing what to do, I started reading Gauss's 2 memoirs on biquadratic residues. Okay, so when you're bored and depressed, read Gauss. Okay. The first one deals with the number of solutions of ax to the 4 minus by to the 4 equals 1 over finite fields. And the second one with ax cubed minus by cubed. Then I noticed similar principles can be applied to all equations of the form ax to the m plus by to the n plus cz to the r equals 0, and that this implies the truth of the so-called Riemann hypothesis for diagonal equations. So this is an interesting story, actually. I don't have time to go into this, but I would encourage people to look at these quotations very carefully and see how ideas actually get born. So the key idea for the third conjecture is rooted in Weis conjectures. And in trying to solve Weis conjecture, there's a subsidiary conjecture that is needed, and that is that there exists a representation rho from the absolute Galois group into GL2ZL. ZL is the ring of L-adic integers. Unfortunately, the fonts are not coming out neat. I guess this is a problem with moving from one version of PowerPoint, which was perfectly fine on my laptop, to another version. So the fonts are not coming out right. But anyway, let's ignore that. But I think everybody can understand some representation. So the trace of the Frobenius automorphism turns out to be the value of the tau function. This is the idea that is going to tie together lots and lots of things. Deligne proved Serre's conjecture, this one, and related this to the Weis conjecture, and thereby showing that Ramanujan's conjecture is a consequence of the Weis conjectures. So this is how the third conjecture, that tau of p is less than 2 times p to the 11 halves, was finally proved. Now the interesting thing about Deligne's result is it allows us to analyze divisibility properties of the tau function. The existence of the L-adic representation allows one to study divisibility properties of tau of p. For example, how many prime divisors does tau of p have? Hey, this sounds like the hardy Ramanujan question, how many prime factors does a random number have? So if you think tau of p is a random number, you would probably guess log p, log absolute value of tau of p. But tau of p is bounded by p to the 11, 2 times p to the 11 halves, therefore it should be log p. And sure enough, it is, but if we need what's called Lamar's conjecture, which says that tau of p is never 0. And then there are other questions that are kind of related that seem to crop up. Are there infinitely many primes p such that p divides tau of p? Are there infinitely many primes such that p to the 5 divides tau of p? We don't know the answer to those questions. However, the L-adic representation allows us to discuss an Erdős-Katz type theorem for tau of p. Namely, how many prime factors does, so assume tau of p is never 0, okay? How many prime factors does tau of p have? Well, inspired by the Erdős-Katz theorem that I quoted to you earlier, it's convenient to consider this quantity omega tau of p minus log p divided by the standard square root, standard deviation, which is square root log p. And it turns out, yes, it's again normally distributed. So again, it's the normal distribution. And pi of x here is the number of primes up to x. The only problem is we have to assume the generalized Riemann hypothesis. And this is joint work with Kumar that we did in the 1980s. Right now, my latest PhD student has been working on variations of this. For example, if you take shifts of the primes, instead of looking at tau of p, but look at tau of p plus 1, a shift, all of a sudden, the whole thing changes again. It is not log p, it is 1/2 log p squared. So things change all of a sudden when you take shifts, and it's very difficult to prove actually. It's quite a bit, it's part of her PhD thesis. Now, related to the tau function is the Sato-Tate conjecture, which I want to describe as the final part of this lecture. It was formulated by Mikio Sato and John Tate and augmented in a substantial way by J.P. Serre. And what does the conjecture say? Well, it says the following. We know for now, thanks to Deligne's work on the Weis conjectures, that tau of p is bounded by 2 times p to the 11 halves. So if you divide tau of p by 2 to the p 11 halves, that's a number between -1 and 1. So the question is, as p varies, how are these numbers between -1 and 1 distributed? Are they uniformly distributed, or are they distributed with respect to some other measure? And it turns out they're not uniformly distributed, but they're distributed with respect to what's called the Sato-Tate measure. It's the square root, sorry about this font business, it's the square root of 1 minus x squared times 2 over pi. Now, if we fix the prime and vary over eigenforms, we can ask the same question, how are the numbers distributed? And these are distributed with respect to this, what's called this p-adic measure discovered by Serre. And in 2009, my student and myself proved that you could actually write down a more precise version of this theorem in which an error term actually appears. So this is the theorem. So what about the classical Sato-Tate conjecture? Well, the classical Sato-Tate conjecture is now a theorem thanks to the work of Barnett Lamb, Garrick T., Harris, and Taylor. They've published a proof of this conjecture. It's in many ways a tour de force of the Langlands program. And the result applies to Fourier coefficients of Hecke eigenforms and uses representation theory, algebraic geometry, and number theory. So it's a big contribution combining 3 different areas of mathematics. The contribution of the Sato-Tate conjecture allows us to now go back and discuss what's called the maximal order of tau n. And we can write down very beautiful theorems. Now again, this is the font, the shifts in the font sizes has messed up the formula. Basically, for all n sufficiently large, tau n divided by n to the 11 halves is less than exponential 1 plus epsilon log to log n over log n, which was mentioned in Kumar's talk this morning. And for infinitely many n, tau n gets that big. So we now know the optimal order completely, thanks to the Sato-Tate conjecture, which is a theorem. And then one can write down many other interesting things, modifying the arguments of the BGHT paper and twisting by Art and L series. One can deduce distribution logs with non-abelian conditions like classical Chebotauro density theorem. This is joint work with Kumar and my student Pengji Wang, and the paper has now appeared in the latest issue of the Journal of the Ramanujan Math Society. Thought I should mention that because it's, after all, a journal named after Ramanujan. Now, at the end of his stay in England, Ramanujan became ill and was admitted to a sanitarium. So in the spring of 1917, Ramanujan contracted tuberculosis, was admitted to a nursing home in Cambridge, England. The poor guy had difficulties with diet. He also had some emotional problems. At one time, he tried to commit suicide. So the time in England was not all that rosy. Surely he found solace in mathematics, no doubt about that. But his personal, emotional life was not all that great. He showed some improvement in the fall of 1918, was elected to the Royal Society at that time. And early in 1919, he recovered enough to return to India and shortly afterwards passed away on 26 April 1920 at the young age of 32. Now, there's a famous story about the number 1729 connected to Ramanujan's life, and I thought I'd share that with you in case you already don't know it. When he was ill in the sanitarium, Hardy came to visit him in a taxi. The taxi was numbered 1729. Hard to find a taxi, by the way, with that number, okay? Took me a while on Google to get that picture. On entering the room, Hardy remarked, "I just came in a taxi numbered 1729, which looks like a dull number. I hope it is not a bad omen." And Ramanujan says, "On the contrary, it is a very interesting number. It is the smallest number that can be written as a sum of 2 cubes in 2 different ways." And what are they? Well, 1729 can be written as 12 cubed plus 1 cubed, 9 cubed plus 10 cubed. Now, the interesting thing is 1729 also appears in the Patanjali's Yoga Sutras. The number appears in this following context. 12 seconds of attention is one dhyana. 12 dhyanas is dharana. 12 seconds is one dharana. 12 dharanas is one dhyana. 12 dhyanas is one samadhi. And therefore, if you want to attain enlightenment, you have to be able to hold your mind on an idea for 1,728 plus 1 seconds, which works out to be about 28 minutes. Anyway, here it is, this number. It can be written as a sum of 2 cubes in 2 different ways. Now, Hardy should have known better because 1728 appears in the delta function, which he would have known in the context of the theory of elliptic functions. But it's a nice story, right? We don't want to knock Hardy too much. Now, the interesting thing is, on his deathbed, essentially, Ramanujan discovered Mach theta functions and Mach modular forms. He outlined a new theory of Mach theta functions in his last letter to Hardy. It took mathematicians 80 years to formulate precisely what Ramanujan meant by these functions. Now, I want to point out to you that if you recall, I mentioned that my postdoc, Michael Dewar, and I got a new way of looking at the partition function and derived the formula, partition formula, without using the circle method. And it's largely due to the development of the theory of Mach theta functions. That formula that those guys discovered couldn't have been done without this theory. It took mathematicians 80 years to formulate precisely what Ramanujan meant by these functions. In modern language, the Mach modular forms fit into a neat exact sequence of nearly holomorphic modular forms, and then you get modular forms of negative weights. And then there's what's called a shadow map. You take any Mach modular form, you look at the shadow map turns into a ordinary holomorphic form. And these Mach theta functions were really Mach modular forms of weight 1/2. So Hardy thought all was well when on 12 January 1920 he had received this letter from Ramanujan describing new discovery of Mach theta functions. They're now the subject of the current research, and the Brunier-Ono work we discussed earlier is based on this theory. Freeman Dyson makes the following remark about Ramanujan's last letter. The Mach theta functions, he says, gives us a tantalizing hints of a grand synthesis still to be discovered. It should be possible to build them into a coherent group theoretical structure analogous to the structure of modular forms which Hecke built around the old theta functions of Jacobi. This remains a challenge for the future, and I think this is correct. This kind of prognosis for the future is valid. I think the theory of quasi-modular forms, nearly holomorphic modular forms, Mach modular forms is just now starting, and there's lots and lots of stuff for some of you youngsters who are trying to do a PhD. Beautiful stuff to kind of learn and contribute. So there it is. Ramanujan gave you a certain path to follow. Now, G.H. Hardy writes a rather kind of sentimental passage in his lectures, Harvard lectures. In 1936, Hardy began his lecture series on Ramanujan's work by saying, "I have to help you to form some sort of reasoned estimate of the most romantic figure in the recent history of mathematics. The real difficulty for me is that Ramanujan was, in a way, my discovery." Now, please don't interpret that as some sort of egotistical statement. I think this is really a sentimental statement that Hardy is making, keeping in mind the context of the 3 other British mathematicians that Ramanujan had written to, one saying, "I think you should study proper rigor," and so on and so forth, and the other 2 not replying. So I think Hardy can claim some credit for having discovered Ramanujan in this sense. I did not invent him. So he just tells you, I didn't invent him. Like other great men, he invented himself. But I was the first really competent person who had a chance to see some of his work, and I can still remember with satisfaction that I could recognize at once what a treasure I had found. And my association with him is the one romantic incident in my life. And I think this is a very important passage. I think it somehow, when I read this passage, it endears Hardy to you. You feel that here's a guy who certainly deserves some credit. So here's the story of Ramanujan. Let me finish by quoting a passage from Aurobindo's Savitri, which seems to be appropriate to this particular theme. "On a height he stood that looked towards greater heights. Our early approaches to the infinite are sunrise splendors on a marvelous verge, while lingers yet unseen the glorious sun. What now we see is a shadow of what must come." So thank you very much.
Like to ask questions?
Of the several mathematical themes that you proposed as still ripe for further study and investigation, which do you think is the closest at hand for major development?
I think the theory of Mach modular forms is really now just getting started. And the important thing that I think youngsters should keep in mind is that, see, doing research means you have to be discovering new things. So waiting for some sort of elegantly presented material, finished product, a beautiful book which explains things neatly. If there's a tendency for students to be waiting for somebody to do that, I think that is a mistake. But by the time such an elegant book appears, the theory is finished. So if you want to participate in the development of a theory, you have to get your hands dirty, take on the papers which are hard to understand, try to have seminars on your own, and really dive into these papers, chip away, tenaciously, regularly, day by day. Take a good chunk paper. There are now some reasonably good survey papers. I think some Ono's papers, for example, in the Bulletin of the American Math Society on Mach modular forms are probably a good place to start, at least to get in. And then as far as research problems are concerned, I think they will present themselves as one enters the field. But if you're always a spectator and not a participant, you will never discover anything new. So I think the theory of Mach modular forms is right now, one century after Ramanujan had introduced. Only now the door has been opened in the sense of we understand conceptually what it is. You see, so I don't understand why people didn't realize, well, you have the theory of modular forms. Why did you make it a holomorphic function? Why not a meromorphic function? Why can't you have poles at those cusps? Why can't you develop a theory? And why do you need to be holomorphic? Why not have differential operators? And instead of having holomorphy, just have a differential operator, which is basically the theory of Mach modular forms. And that's how that whole theory explodes, I think. And now people are finding connections to physics as well, black holes and whatnot. So I think there are some good expository articles that I think one could look at. That's one thing, and the other thing is, of course, in the context of, what we've been doing, Chebotarev density theorem, and I think the theoretic representation can be explored further. Tau function is only the tip of the iceberg, but there are more things that one can do with it.
So I have one question. This tau p is 0 mod p. We know it for 4 or 5 primes. So do you believe that the conjecture is true? I mean, for infinitely many primes, it will be 0?
Well, I think there are several experts on that. Monica being one of them, who I think believes that tau never vanishes, and I think there are some good reasons from their side that's the case. Numerical verification is up to what?
10 to the power 10.
10 to the power 10,
Only
yeah.
Five primes are there for which it is tau p is 0, mod p.
Mod p, yeah,
Mod
that's
p,
right. Yeah, but tau of p is conjectured to be never 0.
Yes.
There are now some other conjectures, one of them being Maeda's conjecture about the irreducibility of the Heckel polynomial. Other conceptual reasons, and then I talked about the theory of Mach modular forms. There's also some other connection to the theory of Mach modular forms why Lamar's conjecture should be true. So now more theoretical insight is coming into the picture, and I think the reason we can't solve something is because we don't know the meaning of the conjecture, and slowly the meaning is emerging, and we're making progress toward that. So I'm not going to say is the Lamar's conjecture true or false, but I would say certainly that we now know more about the Lamar conjecture, what it means from the standpoint of the structural theory of modular forms, that we can probably tackle it. And the same applies for the Riemann hypothesis. The Riemann hypothesis is unsolved simply because we don't know what is the meaning of a 0. See, in the case of algebraic geometry, zeta functions attached to varieties, we know the zero, the counting points of the curve mod P is connected to the zeros of the zeta function. We don't have such a similar thing, although people have tried in the case of the Riemann. So it's always a question of meaning. We don't know what it means, and therefore we're unable to solve it. But I think now we know a little bit on the Lamer conjecture.
So if there are no further questions, let's thank the speaker again for the illustrious talk. Thank you very much.